So let's get started, everyone. So welcome back. Looks like the rain has kept some people away today. So we're going to talk about the singular value decomposition today. And this is in this section on dimensionality reduction. We're going to do this, and we have two more sections on clustering and classification. So I would say what's left, well, possibly with the side for the last couple of lectures, and the last couple of lectures are kind of at the end of the semester and aren't going to be kind of stuff we're building on, so things as much. This will probably be the next kind of lecture or two will probably be the conceptually most challenging part of the class. If you've worked with SVD before, it's so it probably won't be as hard, right? But if this is a new concept for you, you're thinking about very high dimensional data. We'll try and think about through geometry, and we'll look at through linear algebra. But this is a part of the course where students have some trouble sometimes. So the good news about it is that the actual doing the implementation should be rather straightforward, though, right? We're going to do this dimensional reduction through the SVD. The SVD is something that you will see on Thursday's lecture how you could compute it. There are many ways to compute it. This has been studied for decades, actually. And the kind of how, when you actually implement it, you call a package that does it automatically for you. What's conceptually challenging is how to work with it, how to understand what it's doing, how to use it in the right way. And so that's what we'll try and explain in the lecture today. And we'll see kind of it's used as kind of the backbone of a lot of kind of data analysis. It kind of has a goal in itself, but it's also used within a lot of other steps. And we'll see a couple of examples with them in the last lecture. The other thing I wanted to point out today on the schedule is that I posted homework 4. Homework 4 is not due for a few weeks, but so let me just kind of walk through it. There are 3 questions to it. The last 2 are going to be about the SVD, and kind of stuff related to dimensional reduction. The third one will be implementing stuff. It should be fairly straightforward to do. The second one is going to be more conceptual stuff where you have to understand the structure of it. The first question is building on the stuff from gradient descent and linear regression. You're going to be implementing how to find the least squares model for linear regression using gradient descent. This has probably been the most kind of the task. We have variants of this kind of every year in the course. That is kind of the hardest kind of part of the assignments each year. It's implementation. It's building on 2 things you've done before in your previous homework: gradient descent and linear regression. So you're going to build on those. You can always run the old linear regression method to check that what you're doing is correct, but you're going to implement it using using gradient descent. We've tried to kind of break it down into a number of steps this year, so hopefully that keeps you all on the right track, but don't wait till the last minute to do this one again. This one, you might want to look at it, try and figure out, and then if you're stuck, ask myself or the T's for help on this one. Again, if you have trouble working out the details of the Python, again, this tutorial linked off here is stuff that might be helpful, but hopefully you kind of figure out how to do all those components in the previous homework so already. But okay, great. So that's where we are in the schedule. So we did not get quite as, I did a bit of a review in the lecture on Thursday, so we didn't get quite as far. So let me go and jump into the lecture. And I want to keep the third lecture on the power method, the algorithm, a little bit more so self-contained. So we'll see how far we get in this lecture, and if we didn't quite finish everything, we'll put the rest into the last lecture on this section. So okay, great. So the kind of the input of this challenge is going to be we're going to think of this as matrix A, kind of as a subset or as an element of ND. That means we can think of this matrix as, this is A, I'm going to write it as a rectangle. It's going to have n rows and D of the columns, and we'll think of each of the rows, AI, as one data point in RD, right? So we're going to have a set of these data points, and the goal we're going to generally be talking about in this section, although we're not going to finally get to that problem until the last lecture, is to find a low dimensional subspace that minimizes the sum of these, the squared errors onto this subspace of these n data points. All right, so let me try and write this up. Our goal now is going to be k-dimensional subspace B here. So this will be a k-dimensional subspace, and I'm going to represent this by a basis VB, V1, V2 up to V. So K, again, we're going to have that each of these VI is going to be a unit vector. Each of these VI is going to be an RD also, right? We're going to have that VI and VJ is going to be 0 for J not equal to I. So that means the different vectors are going to be orthogonal to each other. So if we think of the origin here, then we're going to have so V1 and so V2, right? So we're going to have these two vectors, and here, let me try and draw this a little bit better. V2, and so these are going to be orthogonal to each other. They're going to be at a right angle. So there's someone online who's not on mute. If you can, yeah. Great. Maybe I can make you as co-host so we can take. Great. Then you can, if someone's not on mute, you can fix that. All right. Great. Yes. So thank you. Great. So okay. So that means there's this we can actually think of, there's this kind of subspace here. And if we're in higher dimensions, right, that there's like a third or fourth or fifth dimension coming out the screen here, and we have some data point. This could be AI. Then we want to project this onto the closest point here in this two-dimensional or k-dimensional subspace defined by these basis vectors, right? And in general, what we would like to do is, if there are a whole bunch of these points, this is A1, A2, A3, so A4, right? And we have a whole bunch of them. I want to find this green subspace, a lower dimensional subspace, that minimizes the sum of these squared errors, right? So this point on here will be the projection onto B of AI. That's going to be this point here, right? And I want to write the sum of squared errors between A and B is going to be the sum equals 1 to n of AI minus the projection onto B of AI squared. Okay, and I want to find B that is minimizing this. And remember, we can write the projection onto B of AI as the sum of J equals 1 up to K of the dot product AI dot Vj. That gives me just a scalar value, and I want to multiply it by Vj, right? So for instance, if I looked at just this one point onto V2, it's going to give me some component onto here. Actually, picture might be a little, yeah, probably just onto V2. This light blue point is just a projection onto V2, and I'm going to get, and so the length of it, the distance from the origin, is the dot product, and how far, and then I move it along this vector some amount, and that gives me the actual point which lives in RD, right? So I'm adding up these d-dimensional points, and this recovers a point in RD, which ends up being right here, right? So this ends up being this point here, and I can also project onto this point, and that gives me that point, right? So I get these coordinates, and I can think of this as, this is kind of an alpha 1 coordinate, this is an alpha 2 coordinate, and so I can think of this now, if this is in a two-dimensional space, as a two-dimensional coordinate of this new projected point. Okay, so I can think of this term as an alpha j of AI, right? It's a coordinate in a lower dimensional subspace. But by multiplying by the d-dimensional vector dj, it's living back in this d-dimensional space again. Okay, so this is stuff we talked a little bit about on Thursday. Okay, would reducing from 3 dimensions down to 2 dimensions be considered so trivial? Well, so kind of this is actually useful in some ways. Sometimes we're in 3-dimensional space and we want to kind of draw a picture in 2 dimension. I want to write this, I want to make a poster or a paper. I can only draw in 2 dimensions. What's the best 2-dimensional subspace? So how do we do this? Right? I haven't explained the algorithm yet, but it's going to be kind of, the algorithm is, it's not going to be too complicated, but kind of getting the best answer should not be completely obvious. The best way actually how to do this. Yeah, great, and so we'll see how to do this next. So even 3 to 2, that's kind of the best I can really draw a picture of. You can kind of go from 2 to 1 dimensions. That's kind of a little bit less illustrative what's going on. But 3 to 2 really captures pretty well what is going on here. But this will extend, all the methods will naturally extend to any dimensional space. Starting from any D dimension, say, 100, down to any K, say 8, right? So all the methods will work kind of naturally with that, and we can illustrate them from kind of 3 to 2 here. All right, great. So this is kind of the goal again. And so how we're going to approach this is to kind of the right way to think about this is through a method called the singular value decomposition. All right, and so this is a linear algebra kind of operation. It's built into basically any package like MATLAB, of course, but also kind of the linear algebra package within inside NumPy, within Python. They all basically go to the same actual the same actual code in the back end, written in Fortran in probably the 1960s or so 70s, actually, maybe some in the 80s, but it's old code. This is a really old problem that people have figured out how to optimize a long time ago. And basically the same code that's been really heavily scrutinized and optimized, all of the languages are going to refer to the same code pretty much. At the very large scale, or if you get sparsity or some other conditions, there's a lot of new methods, but at least for this class, and a lot of the cases, you're just going to call a function, and it's going to call the same old code that was written maybe 50 years ago. Okay, so this is kind of a classic sort of technique. And what's going to do, we're going to take a input matrix A, and we're going to write it as the product of three matrices. Let's do U times S times V transpose, okay? So I'm gonna write A, and A is gonna be my input, my N by D matrix. A is gonna be in N by D, and I'm gonna write it as the product of three matrices, and these are a very special set of three matrices that are gonna encode a lot of information. And so we're just gonna assume we can compute this now, and we'll kind of get some intuition about it. So in the lecture today, in the next lecture, we'll look at least one way how to actually compute this, because I think it's illustrative. Okay, the way I like to think about this is by drawing a picture where A as rectangles here, right? A is N by D, and we're going to get out of this these three matrices. This is going to be U, this is going to be N by N. Okay, so this is a much larger matrix. Let's see, S is going to be N by D also, so it's going to be the same shape as A. It actually depends a little bit on, some packages will actually return, and the default in Python actually returns a different shape for S, but I'll talk a little bit about this. And then V transpose. V transpose is over here. This one is going to be D by D. Okay, so I'm starting with N by D matrix. I get these three matrices out of it, and these have very special structure. Okay, so the first thing to point out is that this S matrix, okay, is actually going to be, the interesting part is all going to be on this diagram. So I'm doing this with a tall and skinny matrix where n is larger than d, but everything can kind of works in a similar way if I have d is larger than n. I think this setting is a bit more interesting. But in this case, in S, the only interesting part is going to be on this diagonal, right? Each element here, this might be entry S, J, J. This is on the diagonal. Everything else here is going to be zeros. That's including everything below this top kind of d by d is all zeros. So in some packages, actually, so it'll just return this as a square matrix, or just return this as a vector, because there are only d values in S that actually matter here. These are known as the singular values. Okay, and they're often written as SJJ is written as sigma j. That's often the notation we'll use here. And we'll have that sigma 1 is greater or equal than sigma 2 up to greater or equal to, so sigma r. And then after this, all of the ones after this might actually be 0. So this R, so R and R is less than or equal to D, right? So it could be that the smallest ones are actually 0 here, but they're in sort of order. So the largest one is in the top left corner, and they're decreasing in order. And this captures some notion of the importance of some stuff that we'll see in a second. Okay. The rows of V transpose, so the columns of V, it's often returned as V transpose. The rows of V transpose, we'll call these Vj. These are the right, so singular vectors. Okay, and these are going to be all. This is V is going to be an orthogonal matrix. So we're going to have that Vj is going to be, the norm of Vj is 1, and we're going to have Vj, the dot product of Vj and Vi is going to be equal to 0 for j not equal to I, right? So this is going to be an orthogonal matrix. And we'll see that this kind of allows us to change the frame of reference. It's kind of like a rotation of all the data. There are a variety of ways of thinking about what's going on here. Okay, so these are going to be these orthogonal vectors in here. So these don't have any scale information. So when I multiply by an orthogonal matrix, a vector by an orthogonal matrix, I don't change the length of that vector. It's just kind of changing a basis. All the length information from A is jammed into this S matrix. That one is going to have these singular values are going to control something about the scale. Okay, and then with the U matrix here, the columns here are going to be interesting. We'll call this Uj, and this is called the left singular vector. Okay, and when you talk about a tall and thin matrix, the left singular vectors are going to be kind of less sort of interesting than the right singular vectors. Okay, so we'll focus a bit less on these. Although, you know, you can look at the analysis of a transpose of A, and then the left singular vectors become more interesting. So it's just a matter of your perspective. All right, so this is more just kind of shape and notation. What is the output of the singular value decomposition? It's going to give you back these 3 matrices, and if I multiply them back together, I should recover U. These left singular vectors this is also going to be orthogonal, so Uj is also going to equal 1, and Uj dot Ui is going to be 0 for I not equal to j here. Okay. and yeah, so I'll write one more fact that we'll want to use later. To understand the importance of the singular values, so this, each of the right singular vectors is a direction in RD, right? So each VJ is a direction in RD, right? So this is in RD. This is the same space as the data, right? So I can think of, you know, there's some space that's going on here. And when I multiply A times Vj, if I look at this, this multiplication, I'm going to get back exactly so sigma j. Okay, so that there's kind of this correspondence, right? So this one element, so sigma j, when I multiply A by Vj, I'm going to get back this value, so sigma j. And I can similarly say that Uj times A, now this is on the left-hand side, in order for the matrix multiplication to work. But if I multiply, I get back sigma j. If I take the norm of the vector, right? A vector matrix multiplication gives me back a vector. And in the first case, where I multiply by Vj, I get back an n-dimensional vector. In the second case, I get back an e-dimensional vector. But either way, I take the norm of it, the length of that vector, right? And that length corresponds exactly with this, so the j, so singular value. Okay, so that's a little bit intuition of how to think about these. We'll see a bit more of this. Okay, so that scale is capturing something about the scale of A here. Okay, the size of A, if I look at multiply by direction, how much scale am I getting out? Okay, okay, this is okay. So this tells me something kind of about the decomposition, but you don't have a lot of intuition of why this is interesting or important yet. It turns out this is a fairly kind of, as long as you don't get these weird ties in the singular values, this decomposition, there's only one unique way to get it with this structure. And this one unique way is going to have a lot of nice kind of properties of it. Okay, the first, so I'm going to start with some geometric intuition, and then we're going to go back to the linear algebra. The first thing I want to talk about is some way I like to think about this as the shape of A via the SVD. Okay, and by the shape of it, I want to think of, again, let's just look at this in R2, or it might be higher dimensions, you know, but the other dimensions aren't going to be as important here. And we're going to get some data points. Each of these is going to be AI. Okay, we're going to think we have some data, and each of these is a row of A, right? So this is a row of A is each of these data points. And I can draw it in this d-dimensional space. Okay. Now, to think about what these right singular vectors are representing here, we're going to think of this will be something like V1, the first right singular vector. Okay, so it's a unit vector. So we know that there's this kind of unit circle, this circle of radius 1, right? And it's sitting on this circle. This is V1, and this V1 is supposed to capture kind of the main direction of the data. If I were to look at the variation kind of from the origin, which direction is the data varying the most? That's kind of what this is capturing. And then V2, I've happened to draw these kind of in the plane a bit here. V2 is the direction with the second most variation, but such that must be orthogonal with V1, right? So these have to be orthogonal with each other. They might be living in 3 or higher dimensions here, but we can always view them in the plane. Right? We can always think of them in these 2 dimensions defined by the span of V1 and V2. Okay. Okay, now to understand and so this also sits on the unit circle. Okay, so I've captured something about the direction. V1 is the most important direction. V2 is kind of like the second most important direction. I want to capture something about the scale here. So to capture the scale, I'm going to think of scaling it by the first, singular value. Okay, so I'm going to think of another vector coming out here. This will be kind of like sigma 1 times V1, and this will be sigma 2 times V2. Okay, so I can kind of think now I've scaled them by the singular values. And if I were to kind of, so this kind of gives me a scale along these 2 directions. But there's this kind of other aspect here that there's kind of this elliptical shape. It's supposed to be, if I drew it okay, it's supposed to be a perfect ellipse. Okay, it's a perfect ellipse that's centered at the origin. Okay, this is an ellipse assuming the center is at the origin. That's supposed to capture the shape of the data here. And the way I like to think about it is I've got a unit vector x, so like another unit vector, right? So it lives on the circle. And I want to think about the quantity a times x, then the length of this quantity. And I know that the length of the quantity along V1 and V2 is going to be exactly the length of the singular value. That's from this property I mentioned at the top here. So I know that this red ellipse, that length is kind of measured along these axes exactly goes to the tips of the green vectors here that have been scaled, but I can actually draw this ellipse, and this is true for anywhere along here, that if I were to draw this in this direction x, the length in this direction is actually kind of the multiplication of a times x norm. The norm of a times x will give me this sort of ellipse. Okay, it's similar to the equation of a circle, right? The equation of a circle, the radius is equal to some kind of the sum of the squared distances from some center. In this case, we're assuming the center is the origin. Okay, so there's some kind of this ellipse, and this ellipse kind of conforms to the shape of the data. There are more data points stretched out along this direction, less so here. Maybe there's a third dimension, but there's very little kind of variation there. But I've only drawn the first 2. There might be a third dimension of this ellipse. And so this gives me kind of the equation of an ellipse defined by here. Okay, and if I want to fit the data and I just stretched it along the coordinate axes, the original black axes, to try and fit an ellipse on the data, I can't do it because the coordinate axis only allows me to stretch along these restricted ways, and that doesn't really fit where the data points are. So the right singular vectors allows me to change the basis, to change the frame, and then I can stretch along that frame. Okay, it's this kind of shape of data is one thing that's captured in this structure here. Okay. Okay, that's one way of thinking about it. Let's look at a little bit more concrete way of thinking about it. Okay, so I've got this example preloaded. Yeah, so if you thought I was just doing these lectures on the seat of my pants, I actually put this in here ahead of time. So this is a simple example. This is a matrix A, right? I have up here with these, there's 4 data points in 2D, right? So if I look at one of them here, 4, 3, well, that corresponds with this point right here, right? So this point is A1. That's the x coordinate is 4, the y coordinate is 3. That gives me 4, 3. right? And there should be some sort of kind of, I can kind of see similar to the other picture. This is a much smaller example, but I've gotten, there's still this kind of elliptical shape of the data along the x equals y axis, something kind of like that. Okay, and now I've gone and I've computed the SVD here, and I've written it out, right? You just look at these, and I've rounded the numbers a little bit. They go on. Just looking at this doesn't, just looking at this U matrix doesn't look that helpful. The S matrix again is interesting, right? It's got all the zeros except on the diagonal. The upper left corner, 8.1, is bigger than 2.3, and V matrix again is a bunch of numbers. Let's go and see. Let's kind of play with these numbers a little bit and see some stuff that happens. Okay, and I want to examine this by what I'd like to do is consider a unit vector. We'll call this X, and it'll be a unit vector in R2. And as an example, let me walk through approximately 2.43, 0.9, so 70. This isn't, if you square those and add them up, that's approximately 1. Okay, so this will be my example here. And so what we're going to do is we're going to draw some pictures. And we're going to see what happens. Yeah, so what I want to do is look at AX, but I'm going to write this out as not A, but remember A I can write as USV transpose X. Okay, so we're going to look at what happens when I do V transpose times X, what happens when I do S times V transpose times X, and we'll kind of walk through this product, and we'll see the effect of each of these matrices, right? Okay. So we'll start with a unit circle, approximately, and we're going to have X is about here, right? So this is about our X. Okay, it should be on the unit circle and about 2.4 and about 0.9, right? So it's about in the right spot. Okay, all right, and so we're going to first multiply by V, and if we remember, let's look at V here. The rows of, well, okay, this is V, but we'll look at, turns out they're the same when you're 2 by 2. You often get things that are the same. V, so we want to consider the columns of V, which are the rows of V transpose. Okay, and so I'm going to multiply. This guy is going to be V1. Okay, and let's look at what is this vector V1. Okay, the x coordinate is -8, and the y coordinate is -5.8. Okay, so that means V1 is about down here, V1. Okay, this is about V1, right? And V2, it's going to be orthogonal to it, and the x coordinate is negative about 5.8, y coordinate about 0.8, so this will be about V2. Okay. Okay, so this is the initial picture, x times V1 times V2. We're going to do this. Okay, we're going to multiply by V transpose times X, and we're going to get another picture over here. Okay, now what's going to be interesting is the first the first coordinate, the output of this is going to be another 2 by 2 so vector, right? I multiply a two-dimensional vector by 2 by 2 matrix. I get out a two-dimensional vector. The first one is basically, I can think of being times v1. The first coordinate I'm getting out is I'm dotting x with v1. Okay, and dotting x with v1 gives me a value of about, so I'm going to say that P is going to be V transpose X, where P is going to be equal to V1X, V1 dot X, and the second coordinate is V2 dot X. Okay, so the first coordinate is going to be, I'm dotting with V1, and I can think of this as taking here and I project onto here and I take the length here and it's negative because it's going the opposite direction of V1. So I'm going to get a negative value of, so the first coordinate is going to be somewhere about over here. This will be about, the first coordinate is going to be about here. And the second coordinate, I'm dotting on the V2. It's a positive coordinate, maybe about 0.6 or so, or let's see, or it's about 0.4. So it's, yeah, so it ends up being about right where P is. This is the second coordinate dotted onto V2, right? So this is dotted onto V2. I get the second coordinate here. And so P, so this, the length of this second projection is the Y direction here. This corresponds with V2, and I get this point P. It's got this new coordinates. This is P is the output. And one thing we'll see if I did this correctly is that there's still, P should lie still on the unit circle. Multiplying a unit vector by an orthogonal matrix is going to give me back a unit vector. So it's still on the unit circle. And basically what I've done is I've changed the basis. Yeah, so I'm getting back that the length of P is still equals to 1, but I've changed the basis, right? Instead of being in the original coordinate system, which I've shown here in the left, on the right, I'm going to be in a new coordinate system defined by V1 and V2. Okay, so I've changed the coordinate system here. That's all. I've kind of just rotated. So if I had another point, it's just going to kind of be changed in the coordinate system as well. If it started on the unit circle, it'll stay on the unit circle. So it's going to move kind of in accordance with X has been mapped to P in a similar way. Okay, it's kind of like a rotation. You can kind of think of this as a rotation of the space, but because I projected onto the negative part of V1, there's kind of like a mirror flip that's going on as well. So you can think of it as doing a mirror flip and then a rotation. So that's orthogonal vectors are rotations, but sometimes they have a mirror flip as well. Okay, what's the question? X is unit vector in the direction of the point. Well, no. X is, X is a unit vector. I've just chosen an arbitrary unit vector, 0.243, 0.97. Yeah, great. Okay, good. Okay, good. So this is what I get for this point P by just V transpose X. Now I want to see what happens if I go the next step and I get a point Q, which is going to be S times V transpose X, and Q is also going to be S times P. Okay, so I'm going to get another point here, Q, which is multiplying by this S matrix. Q is technically going to be in R4. Because I'm multiplying a two-dimensional vector times on the right side by S, and the output is going to be a four-dimensional vector. I'm going to draw the first two coordinates, and then I'll explain the next two coordinates. Okay. The the first two coordinates, I can just first think about the top part of this matrix here. Okay, so now we're going to do S times P, and we're going to get a new shape here. Okay, this is going to be a diagonal matrix. So I'm not really changing the coordinate systems anymore. This one is really V1, but times sigma 1. And this one is V2 times sigma 2. Okay, so I'm not changing the coordinate system anymore, but I'm scaling them, right? So the x coordinate of P is now being scaled by 8.1, right? So what's going to happen is instead of being about 0.8, it's going to be about 6.5 or something, right? So the x coordinate is going to be out here. This will be the x coordinate. This will be qx, and qy is going to be about 0.4 times 2.3, so it's going to be about 1. So this will be qy, and I'm going to get a new data point out here, pretty far out. It's been stretched. Okay, and what this corresponds to is this kind of, there's this other, so sort of ellipse. So I'm no longer on a unit circle. I've kind of taken the unit circle and I've stretched it based on the singular values, right? The x coordinate got stretched by about a factor 8, and the y coordinate got stretched by a factor, so 2.3. So q is now much further away from the origin. It's no longer on the unit circle. Multiplying by s has been stretching this. Okay? And so this gives me two coordinates, the first two coordinates of q, right? But q has 4 coordinates. What's going on with the other 2 coordinates here? Let me see if there's in the chat. Yeah, it's just a convention to write V as V transpose in some cases. In this case, V and V transpose are the same. So when the right singular vectors of V transpose are the rows of V transpose, but they're columns of V. But when I multiply stuff back together, I want to talk about the rows of V transpose when I get U times S times V transpose to recover A. But those rows are what have the orthogonal properties. So that's why I write it as the transpose instead of the columns. Okay. Hopefully to answer the question. Okay, so what happened to the other 2 coordinates of Q? What are the other 2 coordinates of Q here? Yeah, the other 2 coordinates are 0, right? So there are now some other kind of 2 more coordinates which are coming out of the plane here. They're coming out, but for anything that started in the plane, I'm multiplying them by zeros in the S matrix. So these are going to be 0 coordinates. So in some cases, we don't even write these down if we know they're not going to be there. But there are 2 more coordinates in Q, and that means it's 4-dimensional, and I can multiply it by U. And when you multiply it by U, it's kind of mapping it back to the individual rows of A, as opposed to capturing the aggregate properties of it. Okay, so that's kind of how you can think about what U is doing. It's a bit harder to see in this picture, so I'm not going to try and draw it. But okay, so this is I think the most important conceptual part for the shape of the data is that V is giving you a new basis, right? It's transforming the basis into being the right singular vectors, and S is stretching it to say how much data is corresponding to it. And that's how I get this shape, which is the ellipse. All right, in a different basis. If I stretched in the original basis, I couldn't get the ellipse to fit the data. So I have to rotate it first, and then I can stretch and I can fit the ellipse onto the data. Okay, so kind of a geometric view of what is going on here. So maybe really quickly, let me just show you in Python how to do this. yeah, so built into SciPy is this kind of the linear algebra that you need. We can load in our matrix A, and we can call the SVD, and the output of the SVD will be three things, right? U, S, and V transpose. I've written S as a lowercase s because it is its output is a vector as default. You only have a vector worth of data, so it doesn't store the zeros. And if I print these out, you can see that U again is this full matrix. S is just a single row here, 8.1, 2.3, and V is this is a matrix. And right, so S is just this vector. V transpose just the matrix. Okay, and if I take X and I multiply it, I've kind of, okay, that's my input. Let me force normalize it so it's exactly unit vector, right, or up to precision. And then I do V transpose dot X, and I get back P, which is this vector about where I drew it, negative 0.76, negative 6.4, and the norm is 1, just like we intended, multiplied by S. Okay, so what I've done is I've turned this back into a 2x2 matrix here, a diagonal matrix, so that I can multiply it. And this gives me the first two coordinates here of Q. Right, I get the first two coordinates back about 6.2 and negative 1.49. I guess there must have been a sign flip someplace. But now the norm has stretched it here. In order to get it to multiply it by the U matrix, I need to concatenate some zeros here. Okay, so I concatenate some zeros, and then I can multiply it by the U matrix, and I get back as the output I've added the zeros, and I get back a 4-dimensional vector, and we can check that this is the same thing I get if I just multiply it by A, right? A dot X, I get back the same as if I did it by the pieces. Okay, and one more thing to check. If I concatenate the zeros back on S, right, and I multiply these three matrices back together again, I actually am recovering A. Okay, so kind of a little insight into the Python. Again, very straightforward. You'll be asked to do some stuff like this, but it's, it should be, once you get around the way that S is represented, it shouldn't be too hard to work. Okay, and that's linked off the web page. All right, so let me talk about rank K approximation. So I've said, let's bring this back to saying solving this problem of the best least squares dimensional reduction problem. And we're almost going to get there today. Okay, and we're going to instead talk about how you could draw from the SVD the best rank K approximation. We'll go see this through linear algebra. Okay, and the way to think about this is that we're just going to take the top right singular vectors and values, the largest K of them. Okay, well, let me kind of a preview of this. We're going to go back to this shape, and we're just going to turn the bottom part of this diagonal on an S into zeros, and we're going to get kind of a rank K, a low rank approximation, which is a low dimensional approximation. Okay, but let's kind of work through the linear algebra of why this works, and specifically how to think about this. And I want to first think about the error for one kind of so data point A in RD. Okay, and we're going to think about A minus the projection onto B of A. and we'll work in the squared term, right? So if I have one data point, I'm projecting onto some basis B, right? How much error do I have here? Let's just kind of write this out. And remember that I'm going to write VB as V1, V2 up to VK, right? So now I can write out this as, I can write out A's representation as J equals 1 of VJ A VJ dot, right? Minus okay, so what's going on here? I've written out the projection onto the basis B. Remember, I can write this as over the K vectors, V1 through VK, in this basis, the second term here, the dot product, that's the length, times the direction of the vector, up to the K term. To get all of A, I basically need to do this up to D. Okay, so the difference here are how far I'm doing this, and I'm kind of assuming that there's also VK plus 1 up to VD, and these complete the basis of our D. Okay, so these complete the basis of our D. Okay, so I can always pick a set of D orthogonal vectors that complete this basis, and then I can use this to write out the value of A here, right? So this recovers A, and this is the projection of B of A onto B. Okay, and so you see that the first K terms of these sums actually match, right? So what is left here is this norm of J equals to K plus 1 up to D of VJ A VJ, because the other terms cancel, and actually so these are, now I'm adding together these orthogonal vectors, and by the Pythagorean theorem, right, I have VK plus 1 and VK plus 2. These are orthogonal to each other. So if I'm adding up vectors, I can decompose by the Pythagorean, right? Remember, this vector, the sum of squared distances to this vector, right, is the hypotenuse is the squared hypotenuse is the sum of the two lengths, right? So I have h squared equals a b equals a squared plus b squared, and I can do this for d minus k times. So I can get that this is equal to j equals k plus 1 up to d of a, the dot product of vj squared. Okay, so I can drop the norm squared and these unit vectors, which are all orthogonal. Okay. Okay, so I can write the squared norm of this as decomposed onto the residual, the parts that are not included in the basis B, the part that completes the basis. Okay, so I can write out the error here in this way. Okay, but really what we'd like to do is to do this for a sum of data points, right? So I want one other property here. I want to remember that if I take for some vector here, I can think of this as the vector a1 dot v, a2 dot v, an dot v, right? If I do a times v, I get out an n-dimensional vector, which I'm taking the squared of, the squared norm of this vector, and the squared norm is just the sum of the square of the components, right? So this is also equals to 1 to n of ai times v squared. Okay, so this is a separate observation that I can decompose A. Now I have n components. Instead of just one component, so one vector, I've got n of these, and I can decompose this into the sum of n parts for a single vector. Okay, so now I can combine these two properties together, right? The first one that I got to in blue is for a single vector A, and it gives me onto a basis, I get a sum. The error is the sum of the vectors over the vectors Vj. And for a full matrix A, where I have n vectors with a single n data points in a single vector, I can get that as a sum of each data point times the vector. So now if I write this together, what I'd like to write is the A minus the projection of B onto A, right? So something like this. And by this, I mean the sum equals 1 to n of AI minus the projection of B onto B of AI, right? So this is my error that I would like to bound. And I can write this as the sum equals 1 to n, right? That's the same sum minus or time. Each of those terms is the sum of v equals k plus 1 up to d of ai vj. Right? So that's just bringing down the terms inside the square. That's from the first approximation. Okay. And I can change the order here. J equals k plus 1 up to d. And so I'm putting the sum over n on the inside, and the sum over n is actually a times vj squared. Right? So I've swapped the order of operations here. And this term is actually just equal to k plus 1 d. If you remember, what does that term equal? The norm of a times vj squared, or the norm of a times vj. Those vj's, if those are the right singular vectors, then this is then that's just the singular value squared. Okay. So this is exactly equal to, so if I chose these vj's to be the right singular vectors, then the residual error, the error that's left after I project onto the rank k basis I get here, is going to be the sum of the singular values starting after k. Okay, and those are going to be the small ones, right? So it turns out that the SVD, I chose those singular values to have the most variation, right? So the first one is going to have a sigma 1 value is going to be greater than any other possible value. So I'm going to take that, remove it, find the second one that's orthogonal to it, and remove that component, and this is the error which is left. Okay, so the singular value decomposition, if I use just the top k right singular vectors, kind of if I write the sum of squared error of a b equals to let me just write it up here. Okay, and then we can say that the arg min b, where this is k dimensional, of the sum of squared errors of A and B. This is going to be equal to or the, let's say VB, V1 up to VK, then these are going to be equal to the top K right singular vectors of A. Okay, so the optimal, the set of B, which is minimizing the sum of the squared errors, are going to be the top right singular vectors of A. Okay, this is, yeah, if I'm describing this as a basis in this way. Okay, yeah.
Why is the logarithm of
K plus, oh, great, yeah, this should be, thank you, this should be K plus 1 up there, right? Good, thank you, just, I missed that one dash. All right, okay, so this gives me the kind of the best solution here. In this sense, it's not quite what we wanted at the beginning, the best dimensional reduction. We'll get back to that. That's going to be a simple trick, but we'll see that with PCA, which will come after we see how to compute all this stuff. These are effectively described as a basis, which are vectors coming from the origin, and there's some kind of hidden assumption there that we will see how to remove later. Okay, so what I want, another perspective on this is that I want the rank of B to be equal to K, the rank of B. So B is going to I've kind of been nebulous about exactly what B means. I've said, well, it's defined by this basis of these K vectors, these K orthogonal vectors. I often want to find the best rank K approximation of A. So we're often going to say A sub K is going to be the best rank K approximation of A. So it's going to be a matrix AK, and this is sometimes what we think about as B. This will be a matrix, which is going to be a rank K matrix. A might be rank D, right? D is less than N. So it might have a much higher rank. So I want to have a rank K matrix here. And so by best, I can mean two things here. Best, I can either mean min A minus AK so the Frobenius norm, okay, where I look at the Frobenius norm of the difference between the two matrices, or you can also say the spectral norm. Okay, so either let me write this a little bit more clearly, either the Frobenius norm or the spectral norm, and we'll see that the SVD gives us for either of these, it gives us the best answer. The best answer is going to be the same. And this matrix, A sub K, I will kind of, one way you can write this as J equals 1 up to K of sigma J Uj Vj transpose. Okay, this is one way of thinking about of writing this, and these are Vj again is the right, so this is the right singular vector. This is the right singular vector. Again, the sigma j is going to correspond with the singular value. And now I need this other term here, right, this uj, and this will correspond with the left singular vector. So this is where I need the left singular vector is a uj term. Okay, and so yeah, I can think of this as sigma 1 u1 v1 transpose plus sigma 2 u1 u2 v2 transpose, and so forth. And I think it's useful to kind of pause here and think about what does this object look like, right? Getting AK, and I'm adding together these terms, right, in the sum. What does this sigma 1 u1 v1 transpose, what are the dimensions of that? Sigma is a scalar, so that doesn't do anything with dimensions. U is a column vector, an n by 1 column vector, u1, and v1 transpose, right? This is this 1 by d row vector. Okay? So I have an n by 1 times a 1 by d vectors. So what's the dimensionality I'm going to get out of this? Yep. Yeah, right. So this is an element of n by d, which is good because a sub k, I want this to be n by d, and I'm adding these up, right? I can do element-wise addition. I want to look at a minus a sub k. If I use matrix subtraction, they have to match their size, right? So and a was n by d. This is an outer product. U1 times v1 transpose is an outer product, so it blows stuff up, right? But what's the rank of that? What's the rank of that term in purple? So it's the right size. What is the rank of it? Turns out it's rank 1. It's a rank 1 matrix. Okay, it's n by d, but its rank is only 1. Okay, anytime I get something by an outer product of 2 vectors, its rank is going to be only 1. So I'm adding up k of these matrices, each of rank 1. It turns out they're all going to be linearly kind of independent of each other. So they're each adding to the rank. So when I add them up, they're going to be rank k. Okay, and each one gives me a rank 1 approximation. That's the best rank 1 approximation of A. And when I add the second term to it, it's the best rank 2 approximation of A. I get part from rank 1 and another rank 1. And this one has kind of the best shape of it, and I'm scaling by sigma 1. That's the biggest term. Sigma 2 is the next biggest term. And that is kind of a different component to the matrix, a different property of it. Kind of way that it evolves, and that term is not quite as big. And I'm adding these progressively because the sigmas are smaller, and so those terms aren't as meaningful in approximation. Okay. Okay, well, let me go and explain a little bit about how to think about these. Yeah, I guess another way of thinking about this is if I want, remember, if I had this matrix A and I got this decomposition based on the SVD, this is U, this is S, and only on the diagonal is interesting. And this is V transpose. Okay. And now I want to switch this up and get a best rank K approximation. Okay. Well, let me make a couple of observations here. First off, anything, this is D minus K rows here. these rows are pretty much uninteresting because they're being multiplied by all the zeros in here. And when I recover A, these are multiplied by 0, so these are kind of uninteresting. And what we're going to do to get the best rank K approximation is we're going to go and we're going to zero out these terms as well. So I'm only going to keep K of these terms, right? So now what I'm going to do is I'm going to also set this now becomes all zeros. So this terms are also all zeros. So I only have K terms left here. And that's the same thing is going to happen here, that these are not going to matter as much either, because they're now also going to be multiplied by the new zeros when I'm recovering this, right? So I'm getting here, this term is V1 transpose, V2 transpose, and so forth. Those are the top K right singular vectors. I have the top K singular values. These are sigma 1, sigma 2, and then finally I'm going to get these left singular vectors, U1, U2, and so forth. And everything after the kth one, I'm basically dropping, and all I need to do is zero out the singular values. I zero out the singular values that I don't care about, and I multiply it back together again, then all those other kind of the highlighted, you know, light blue and purple parts are just kind of multiplied by zeros, and those go away. And so the result is rank K. Yeah.
What is the big part of read? Because I'm seeing use for that part that you were.
Yeah, so it's useful in that, you know, it turns out it's not that useful, right? What I know about it is that the column vectors are orthogonal with the column vectors, right? And so they're unit vectors. So that allows me to recover the elements of A, and it's orthogonal. It's just the convention that it is this property, but those really don't matter. If I looked at the transpose of this, where it was kind of a short and wide matrix, where n was less than d, then all the u's would matter and less of the v transpose would matter, because v transpose would be the bigger part then. So I usually just keep around both, so I can always say they're orthogonal matrices. But you're right; those really aren't very useful. Yep. Great. Yeah. Good. I think I answered that question. Okay. Right. So, so to recover this, either I can just use the rows U1 and V1 and sigma K and just multiply those together as the sum, right? So I can either write AK equals, say, the sum J equals 1 to K of sigma J UJ VJ transpose, right, as I did before, or I can say it's equal to U times SK V transpose, where SK is going to be the diagonal n by d, where I'm just have sigma 1 up to sigma k. Or I can do UK SK VK transpose, where I'm just keeping, where just this top part is VK transpose, just the top K of the rows, and UK is just the first K of the columns here. And that's what that last form means. Okay. So, you know, you can recreate this in multiple ways. Some are more efficient than others, but whichever conceptually is most useful for you. Let me just say one more thing, in that we already derived that A minus AK squared Frobenius norm, and this is what I wanted to minimize. This is equal to J equals K plus 1 D of sigma J squared, right? So I claim that the best rank K minimized for any rank K matrix AK, this for B is norm of the difference between them. And that's just the smallest singular values after K. Another interesting property is AK spectral norm. The spectral norm is that once I subtract them, that's the maximum norm in any direction. Remember, this is equal to max x is a unit vector of a minus ak x squared, right? So this is what this is equal to, and this is kind of a procedural or algorithm or kind of non-constructive definition. I have to maximize overall x. It turns out once I've subtracted it, the maximum x is the k plus 1 singular vector, right? Singular vector. So this is exactly equal to k plus 1 squared. So the spectral norm of the difference, the largest single direction left squared, corresponds with the k plus 1 right singular vector, and its value is the k plus 1 singular value. Okay, so this is why the spectral is referring to eigen and SVD decompositions, and it actually refers to the largest singular value squared, or the largest singular value which is remaining after I factored out the other ones. And that's what the residual, the size of the residual in that way. Okay, great, we'll stop here. We'll probably talk about how this relates to eigen decompositions, and then that'll lead us into the algorithm, the power method, which we'll see one way how to construct this, and then we'll see how to use it in applications and how to kind of completely solve this dimensional reduction problem in the last lecture. Hopefully this gives you some fresh perspectives on this. So this essentially zeroes out the values. I'm reading the comment now. It's essentially zeroes out the values between K and D. Yeah, right. It's zeroing out all those components. It really only needs to zero out the values in S, and all the rest of it kind of the lower rank component gets destroyed in the process.